The brute force algorithm is the last of the algorithms. Well, technically it was earlier in the book, but I saved it for the end because I think that makes more sense to me in terms of the order to talk about these ways of solving it. But let's go ahead and just discuss it, discuss the implications of it. And I mentioned this in class last time, which is that I'm not going to test you on this. I'm not going to make you do the brute force on a test, which I'm not going to change my philosophy on that. But I think it's still worth it to just discuss, how if we were obsessed with finding the perfect answer, if it was relevant, how do we do it? And it's interesting that there is no better algorithm for solving for finding the perfect answer than brute force, which is kind of hard to believe. But anyways, it says to step one, make a list of all the Hamilton circuits in the underlying graph of Kn. And if you're like, what's Kn? Well, get that in a second. But basically, that's just how the book describes. Um, that's how the book describes a graphs of these types of circuits, which we just call complete. I'm going to find that in a second. Step two, it says to calculate the total weight of each Hamilton circuit. Basically, find all the Hamilton circuits in the graph, check the weight of all of them. Step three, choose the Hamilton circuit with the least total weight. So it's very similar to repetitive nearest neighbor in that we're finding a bunch of them and finding the cheapest. But in this one, we're literally finding all of them, and that's obviously something that is not necessarily going to be very fun to do. And so before we get into actually doing it, how do we know if we find them all and how do we find them all? It actually returns back to the same sort of math we did in chapter 2 when we discussed the Shapley-Shubik power distribution. If you remember, we talked about the number of sequential coalitions in a particular weighted voting system as given by the formula n factorial. And it's actually not so different. The math that goes into finding the number of Hamilton circuits is not so different. But let's go ahead and define the complete graphs. It says that complete graph is a simple graph in which the vertices are completely interconnected is called complete. So the key there is that they're completely interconnected, meaning that every vertex is connected to one another. And if I said this in class a few weeks ago when we got into this, but in these chapters, if we're trying to find a circuit between a bunch of different locations, or say we're trying to go on vacation between points A, B, C, and D and go back home, there's always a way to get from any one point to any other point. Since the lines don't represent streets, the line just represents traveling between those points. It doesn't necessarily have to be a direct path. If we want to get from point A to point B, we can get there. If we want to get from point B to point C, we can get there. Basically, it is always possible to travel in between all of them, hence completely interconnected. That's the idea of a complete graph. It's just they're all connected together. It says in the book that they are going to be denoted by k sub n, which is just the way of saying like k3. Sorry if you can't really see this. Let me center mode here. Better. Well, actually, now I'm in the way. There we go. Um, K3 is complete graph of size 3. K4 is the complete graph of size 4. K5 is, let me use my laser pointer. K3, size 3, K4, size 4, K5, size 5. Basically, it's just a way of denoting how many points are in my circuit, how many places do I need to go to. And so, like, say I had to go to 12 different places in my vacation or in my business trip. That would be K12 or whatever. And basically over here are some of those key properties. This is also in your packet if you want to have if you want these things printed out. But basically the degree of every vertex in Kn will be n minus 1. That's kind of obvious because if it's completely interconnected, say for example K6, it's going to have 5 locations we can go to. So the degree of vertex A will be 5, meaning it's odd as opposed to even. Also, if we were going to go back into chapter 5 and talk about Euler circuits and stuff, notice that this graph would not have an Euler circuit because all the vertices would be degree 5. Odd. But actually K5 would have an Euler circuit because every one is degree 4. 4 is even and even is good. Anyways, sorry, I'm getting distracted. We're not trying to talk about chapter 5 right now. We're in chapter 6. Focus on chapter 6. But anyways, it also talks about the number of edges and blah, blah, blah. Not really relevant. But what is kind of relevant is the number of Hamilton circuits in Kn is given by n minus 1 factorial. So for example, say I wanted to travel between, formulate Hamilton circuits starting at A and going between all the different points in this graph as we were via nearest neighbor algorithm. Notice I could say go A, F, E, D, C, B, A. That would be one potential Hamilton circuit. But there's going to be a whole bunch of different ways to do that. I could go A, E, B, D, C, F, A. Notice that if I'm starting from A, there's 5 locations. So the first set of choices, like when we're running on an A, is I had 5 targets, 5 places to go. That would be 5 potential options. Then from the next point, I'm going to have 4 potential options, then 3, then 2, then 1, and that will finish my nearest neighbor algorithm. But what that gives me is 5 times 4 times 3 times 2 times 1, which would be the same as this formula if I were plugging in 6 in there. Let me move back to the whiteboard because I want to try to write what I'm saying, because I don't know if this is making sense as I'm saying it. Um, so let me zoom in a little and start my highlighting. So my point, what I was trying to describe is why is the number of Hamilton circuits given by a factorial? It's very similar to Shapley-Shubik, because if I'm starting at A, initially I have 5 choices. The fundamental counting principle says that if we have a series of various different choices, like from A I have 5 choices, 5 different places I could go to. Well, really, if I was trying to write those Hamilton circuits out, I could go A to F, or I could go A to E, I could go A to D, I could go A to C, or I could go to A to B, right? If I'm starting at A, I first have 5 choices. From there, I would have 4 more unique choices. So I could then, from F, I could either go to any one of those locations. So I could go A, F, which would then go to E, or C, or B. From E, I could do the same thing. I would have 4 choices. And basically, I'm going to have 5 choices. Each one of those stems to 4 new choices, which would be 5 times 4, 20 options. Then I still have 3 locations, but essentially what we're getting is a factorial pattern of 5 choices times 4 choices times 3 choices, 1 choices. And in this example, K6, um, this is how many Hamilton circuits we would get. Basically, it's just a permutation of every letter. It's just like Shapley-Shubik, exactly the same thing. N factorial gave us the number of sequential coalitions, but actually notice it's n minus 1 factorial instead because A was fixed. We're starting at A and we're ending at A. We had 5 other points to permute in that list in order to find all the coalitions. Now, technically, you could have started at B, D, C, F, and E. I don't know why I did it in that order, but as well. But as I was saying, those would all be the same answers because they, uh, even if I started at B, if I run all those permutations starting from B instead, they're all just going to be duplicates to all the ones I found from starting at A. And actually, as another just tip for you is in, so if we do that math, this would be 5 times 4 is 20, times 3 60, times 2 is 120. 5 factorial is 120. And that would be how many Hamilton circuits we have in that graph. So if circling back to the brute force algorithm, if we're running the brute force algorithm, we have to find all the Hamilton circuits. Well, even if we just have 6 points, we're gonna have to find 120 unique options in order to run the brute force algorithm. So if we thought that the repetitive nearest neighbor algorithm was bad, where we had to find 6 options and choose, so like in my opinion, that was enough. That was more than enough work. That was a lot of work already. We're gonna have to find 120 if we were going to do force. Obviously, I'm not gonna do that here because that would take forever, and I would hate my life, and you would too. But I just wanted to get at the gist of what is the issue with the brute force as well. And just another side note is that actually, if we look at all those 120 circuits, half of those are all going to be duplicates because as we run through every permutation, like say for example A, B, C, D, E, F, A, each one of those would be duplicated by the reverse circuit A, F, E, D, C, B, A. And so actually, if you want to know how many uniquely costed maximum uniquely costed options, that would just be that divided by 2, which would be 60 uniquely costed. Well, technically they're not still going to be uniquely costed, but you can kind of cut down on the reverse circuits if you wanted to. That's actually not, the book doesn't get into that, I don't think. Um, but whatever, I thought it's worth mentioning. Also, if you're wondering how would I remember all this, really you could just remember in this formula, if it's 6 vertices, subtract 1, like so n is the number of vertices in the case, so n would be equal to 6 in that example. Basically, we're just going to plug it into n minus 1 factorial, which would be 6 minus 1 factorial, 5 factorial, which again just means 5 times 4 times 3 times 2. And again, you can skip the times 1 because it's not going to change the value. That's a good stopping point for this one.